Hello and welcome. My name is Matthew Hershey, and I'll be one of your instructors today for the data science symposium here called Counting COVID. I am an associate professor in the Department of Medicine in the Division of Endocrinology, and I run a lab at the Duke Molecular Physiology Institute focused on metabolism. I'm joined here by Akshay Bareja. Akshay, please say hello.
Hey Matt, I'm Akshay. I work in Jim White's lab, also at the DMPI, where we do aging research in the context of skeletal muscle biology.
Great. So today is the first lecture in a series of lectures. The purpose today is to introduce the general field of data science, some general concepts about data science, and then use some specific examples counting and tracking COVID-19 cases. The purpose here is not to take a deep dive into the mechanics of data science and have you code along with us. If you're interested in that next step after today's lecture, then I'll direct you to some online learning resources that Akshay and I have developed at the end of today's class. We'll have approximately an hour to an hour and 15 minutes of content for you today. And I'll just let you know that if you can't stay for the entire lecture today, then we'll post a recording of it online and send a link to all the registered participants after class. Importantly, I'll also mention there are several other lectures. Like I said, this is the first in a series that will cover a myriad of topics related to data science and to analyze COVID-19 data. As I will begin today's lecture, and Akshay then will take over for me halfway through. Akshay will be manning the Q&A window. So if any of the participants have questions as they arise, feel free to use that Q&A window and we will try to answer them live while we're going through class. And so with that, I'd like to just go ahead and start today's lecture. All right. We call today's lecture Counting COVID, Key Elements of the Analytical Toolbox for Understanding COVID-19. So we saw at the beginning of this year, COVID-19 rapidly infected people across the United States. This image is called a hexbin chloropleth graph that shows the increase in COVID as the date increases over time in the different states here. This is just one type of data that's been generated quite rapidly for related to COVID-19. But we have several different types of data that we've seen really a literal explosion. We've seen infection rates and infection prediction rates by epidemiologists. We've seen data generated by basic scientists related to sequencing, molecular biology, and even drug leads. We've seen an explosion in translational data, quite importantly, preclinical phase 1 and phase 2 data rapidly moving towards treatments and vaccines. We've also seen clinical data from patients who have been admitted and treated with COVID-19, such as chest CT images. And then finally, perhaps the most surprising is this explosion in the literature related to COVID-19, both in the preprint literature as well as peer-reviewed. And so we wanted to put together this symposium and really think about the different types of data that are being generated surrounding COVID-19 and the different types of tools that are available to data scientists that are going to allow data scientists and really people of all walks access to and the ability to analyze the data. So this rapid emergence generated several healthcare decision-making challenges. So first, I would say there's a volume. The rapid data collection and storage allowed access to huge amounts of medical information. Ubiquity, the data became available anywhere across geography, social and economic classes. This was really quite remarkable. And then also the latency perhaps is the most surprising, where the technology facilitates no delay and access to the data. We're really living in an unprecedented time for access to these large-scale data sets. And so the question then emerges, how do we make sense of COVID-19 data to make better healthcare decisions? Well, and this is, again, the focus of this symposium is really about data-driven decision-making. So really, what does that mean? Well, this is a data pyramid where we start with data, and data then can lead to information. Information can lead to knowledge. And finally, that knowledge, when put into practice, can lead to wisdom. So the goal for us as data scientists is really to try to take that data and turn it into information that we can then use as actionable knowledge for healthcare decision making. All right, so one way that we do this is with the emerging field of data science. And data science has had a lot of buzzwords around it. It's got a myriad of different definitions. For historical purposes, I'll show you one of the first definitions. Really, it was this sort of amalgamation of math and statistics knowledge, some sort of substantive expertise, but then also what was colloquially called hacking skills. And when you put all of this together, you end up with something that was called data science, that was neither one of these things alone. Okay, well, that was one of the earliest definitions that's quite dated at probably 10 years old now. And what we have now is several iterations of the Venn diagram of data science. Yeah, here's one that I thought was quite comical. Again, we have math and statistics knowledge. We have hacking skills, we have some expertise, but then also we have intention. You know, how evil is the person trying to do this? So we thought that this was, quite funny, at least from the academic setting. And so we've got this idea of data science where it's this amalgamation of this math and statistics and expertise and computer programming. And when we put this together, we can then take data and transform it into knowledge. And that really is the goal of data science. Now, this is remarkable because the types of data are really not important. And what I mean by that is you can be data agnostic and you can apply these skills to different types of data to really glean information from this. And one beautiful example that we'll be using today is counting COVID-19 and really what can we learn and what can we glean from COVID-19 data? And more importantly, how do we glean some information from this plethora of COVID-19 data to then turn that information from data into knowledge? Well, there are several approaches to this knowledge generation. So new tools allow data interrogation more easily than ever before. And again, this is remarkable, and all of the credit goes to the tool builders who are developing these open source tools that allow people like me, and perhaps even people like you, to perform some of these data transformations that would otherwise have been impossible before. Now, this was quite interesting. The computer programming field has this debate about what is the most important and most popular and most impactful programming language. And you can see in this sort of horse race diagram, this is the most popular programming languages on Stack Overflow, which is a common site for asking and answering questions related to programming and data. And you can see that the differences are changing over time. And of course, it's quite dramatic with this background music. But this is important because you can see some trends and see some shifts. But ultimately, people will sometimes get caught up in which is the most important and the most useful and impactful programming language. But the interesting thing is, if we compare these to a common programming language such as Excel, we could see that there are hundreds of million, or even 100 million Excel users, and this dwarfs all of the other sort of programming languages combined. And so, my point of showing you this here is to really emphasize that the language that you use is not important, but really what you do with it. And that's really what I want to say here is data scientists and programmers oftentimes get caught up in and have strong opinions about the differences in language. And people starting out will often say, well, should I start with this language or should I start with this language? And I don't know which one I should start with. It really doesn't matter. What we're going to do here in this first lecture is we're going to be focusing on the programming language called R. In some later lectures as part of the symposium, we will be looking at Python. We'll be looking at some implementations of Python. But again, at the end of the day, the important thing here is not which language you choose, but rather what you can do with it. And so I'll be teaching you a little bit about the programming language R today. And I want to start by just saying that R is a language, just like all of these other programming languages are languages. And we can think about them as having nouns and having verbs and having syntax and having rules, just like other languages, just like French or German or Mandarin, all have their own rules and signs. So I want to explore a little bit and explain to you some of the early and fundamental pieces that you'll need to know about the programming language R. So R has values. And this value can be a few different things here. I'm showing you 3 examples of a value on this slide. So we have a value, which is a number, the number 1. I'm showing you a value, North Carolina. This is text. This is a string. And I'm also showing you a date here. So these are different types of values, and R has some different types. We'll get into some more specifics in a little bit, but we can remember that R has values. R also has something that's called an object. Now, an object is unique because it's a name, but it doesn't have quotes, and this will become important in just a moment. An object is going to store something. It can be a value, it can be another object, or it can be the result of a function. And we can think of an object as a container that will hold some information for us. And the nice thing is the container can be a lot of different shapes and sizes and have different parameters. Importantly, not infinite, but certainly has the flexibility to hold several different types of things. We assign objects by using this funny looking left pointing arrow that is then going to allow us to put something in our container or put something in our object. All right, so for the purpose of today, we've decided not to have you guys code along and not to have you all perform some of these tasks along with us. Like I said, this is supposed to be sort of a zero-entry introduction to data science and to the programming language R. And we'll point you to some resources at the end of this if you really want to get your sort of hands coding, your hands wet, so to speak. But I will show you a couple of things here. So if we take an object and we say its name and we assign it to a number 4, that's going to then assign this object. If we then say what is name, we can then run this and it should tell us name is 4. And we can do this for anything. Again, name can be a lot of different things. It can be a number, it could be a series of numbers, it could be a word. And we can then call that object and see what it is by just typing name. Okay, so R also has functions. And this is important because this is where the power of some of these data science tools comes in. When we want to do transformations of our data, then what we oftentimes want to do is apply some function to it. So a function is a name without quotes. It's followed by a parentheses, and this is important. This is how R, again, this programming language, identifies a function that you're supposed to run. You're supposed to do something to it. A function will also have some arguments. In this case, it will be some modifiers for this function. So if we have a function that's round, it's going to take a number and then round it, and it will then tell us how many digits we want to round it to, and we can say 3. So the programming language R knows about pi. It knows that pi is a very long number. But if we apply this function to pi, we can see that we rounded it to 3 digits here. And this is a very simple example of a function. The function is called round. It can then take an object. In this case, the object is pi, and it is going to perform a transformation to it. It's going to round it and essentially round it to 3 digits. Okay, so this is how we think about functions. All right, now we'll skip over a couple of these because the most important thing that I want to show you and explain to you is how R stores data. So data are stored in data tables or data frames. And this is important because this is essentially how we are going to interact with a lot of our data within the R programming environment. Now, a data frame is quite conceptually similar to a spreadsheet with rows and columns. So you can see here, this is a sample from the CDC dataset. We'll tell you about this dataset a little bit more in a moment. But you can see here, it's got a column and it's got a row. And the column is going to be states, and starting with United States and then going on to individual states. We have some ethnicity data, distribution, weighted distribution, et cetera. Now, this is what it would look like in the concept of a spreadsheet. Well, this is the exact same data. It might look a little bit less familiar, but if we look closer, we can see that we have state, ethnicity, a distribution, a weighted distribution, and then a row ID. And again, here's row 1, here's row 2, and on it goes. And so this is how R is going to be looking at our data. And this is then how we are going to conceptually think about our data. So we can store this one. So when I refer to a data frame, or when I refer to a table, we can conceptually think of a spreadsheet. All right. Now, within this spreadsheet or within this data frame, we can extract new objects or we can create new objects. So the way that the R programming language calls a single part of the data frame is with this sort of silly money sign here, this dollar sign. So when we type CDC, money sign, distribution, what we end up with is pulling out just the distribution column. So if you recall, distribution was one of the column names that has some data within it. And so what we're saying is, look within this object, and there is a column called distribution, and I want to look at that one only. If we go back one slide, I'm going to show you that this is a table that's 5 by 5. When we move forward now, this is, so it's 5 because I just pulled the first 5 rows, but this would be 185 by 5. Here, this is 185 by 1 because we're just pulling a single column out of it. So that's how you would do that. All right. Now, if we then write this, I'll just copy and paste it just to show you. If we do this, we run this in our little console here, we can see that we can pull these data out, and that's exactly what we would expect. So now this is just a very long list of numbers that then is available to us because we called on it specifically. All right, so we can extract new objects like we did with the CDC distribution, but we can also save this. So if we want to save this as an object, recall the object was really a container. It holds a lot of different types of things. In this case, our container can be quite simply the list of long numbers. So if we take this, and for a time I'll just cut and paste, and we run this, what will happen is instead of showing us all the numbers, what it did is it put this inside of the object called distribution. Now, like before, when we use that name example, if we want to call distribution, we just write distribution, and then we can see all of the elements inside of this object. All right, so this is just a little bit of a flavor, a little bit of an introduction to how to think about data. Data is quite conceptually similar to a spreadsheet. And I showed you a few examples within this, these little code chunk boxes of how to interact with this. Now, oftentimes, data scientists aren't going to be interacting with their data in these code chunk boxes. Instead, they'll be using something called an integrated developer environment, or IDE. All right, so R, the way to think about it is it's a statistical programming language. And we can interface with this by these code chunk boxes. And again, if we wanted to assign an object a name, and mine is Matt, and then we can call name. So this is one way that we can interact with it. But this is not very common. We can think about interacting it this way by analogy of a car engine. Now, when we drive cars, we don't really interact with the engine directly. Instead, we interact with this driver's seat and the console that's telling us about the car, how fast it's going, the different information about it. So there are several different integrated developer environments for different languages. There are even a few different ones for R. We've used extensively one that's called RStudio. And RStudio is going to be a premier integrated developer environment that is free, it's open source, that we won't have time to get into today. But I will point you to this RStudio Cloud. There's two different ways to interact with RStudio. The first is to download the software directly, and then you can install and work with packages directly on your local machine. The other way would be to interact with a new, and you can see that there's general availability later this summer for a product they call RStudio Cloud. So this is a cloud-based environment for data science. And so I put the link here. You can look up RStudio Cloud if you'd like. Again, because of the format of the class today, or the lecture today, we won't get deep into the mechanics of the RStudio and the integrated developer environment and getting you all installed and these things, but really just to let you know sort of what's out there and how to interact with it. Okay. So I see that Akshay is answering some questions on the Q&A board as we're going along. This is fantastic. Again, if there's any questions as they come up, please chime in there. So the next thing to tell you about is something that are called packages. And packages really is where the R ecosystem shines. Now, the R language contains thousands of functions, data sets, and help pages. But interestingly, there's only a few hundred are included when you download R. This is called base R. And base R is going to be the sort of base functions that you need to do most or many transformations. But there are plenty of other functions and data sets and help pages that are grouped into collections. And these are called packages. And you can download some packages that you want or not. Now, the power of the packages come from all of the functions within these packages. So if you're thinking you have some very specific sort of data transformation that you want to do, or some data exploration that you want to do, there's a really good chance that somebody else has also thought of that and has developed a function to do exactly the thing that you want to do. Now, what exactly are these functions? We looked at one earlier. This was round. When we rounded pi to 3 digits, that was a function. The way that we can think about functions is to think of them as verbs. So verbs act on data, or these functions act on data. So here's just a very simple example. We can say, do this. That's the name of the function. What are we doing it to? Well, we're doing it to that. Well, we also said functions can have something we called arguments. Well, in this case, we would say, do this to that using these. Using these would be the arguments, the specifics, like what do we want to do? We want to round to pi using 3 digits. And so this, again, is the simplest way to think about functions and how we want to interact with our data. And it really, I highlight it here, functions are the power of using R. All right, now, packages contain functions, documentations, and data. So if we want to get some packages or some functions that somebody else has developed, the way that we would do that, it was we would download and install a package. So here's one example. This package is called dplyr. In a little bit, Akshay will tell you some specifics about dplyr. But what we can see is that dplyr is a package, and it has several different key functions within it, such as mutate, select, filter, and so on. Again, Akshay will go over some of these in a little bit. And so what we would want to do then is we would want to download and install dplyr in order to get all of the functions that dplyr contains. So the way that we do that mostly is by going to a repository called CRAN. So CRAN is the canonical place that most packages are installed. And we can then download, these are publicly available, free. We can then download these packages, install them into our operating environment. You can think of them as optional extensions of the R language. So again, we have base R, and then we've got all of these auxiliary functions. So if you want to go deep into statistics, there are statistical packages. If you want to do some data science, we'll show you some data science packages today. If you want to do some epidemiology, there are very solid, fantastic packages for doing epidemiology. So again, you can think of these as the extensions that you can then add or subtract from your environment. Okay, so I'll go through this a little bit quickly, but I want to give you a sense of how you do this. So really, it's quite simple. If a package is on CRAN, we use a function called install packages, and then we say the name of the package that we want to install. The important thing is we can do this one time per computer, and this is then going to install the package, the documentation, the functions, and everything along with it. So one package that we will be showing you today is a package called Tidyverse. It turns out Tidyverse isn't a single package. Tidyverse is a bit of a meta package, which is what they call an opinionated collection of packages for data science. We'll tell you a little bit more about Tidyverse in a few minutes. But it contains several different packages. It contains one called ggplot 2, which we'll be showing you today. It also contains one called dplyr and several others. So the pop quiz here is, how would you install all of these packages? Well, one solution would be something like this. Install package, install package, install package, and so on. But it turns out I told you that this is a bit of a meta package because the Tidyverse has made it quite simple that you can install packages Tidyverse. And what it will do is it will install nearly all of these packages for you. It's a bit of a shortcut for installing and loading the most common and essential components of the Tidyverse collection of packages. So if we install the package, that's great. We do this one time per computer. But importantly, if we want to use the functions within the Tidyverse package or packages, we have to call this one time per session. So if you're doing some data science and then you close your session and you go to sleep, come back the next day, and you decide that you want to do the same sort of data science, you need to reload your libraries. And you do this by calling a simple function or simple command called library, and you load this. So this is one time per session. All right, now, downloading a package isn't the same as using it. If you'd like to use a package, you need to tell R to use it. Again, that's that library command that I just showed you. So downloading it is different. Again, this is installing package. If you close R, just to reiterate, you'll need to reload the package if you want to use it again, but you won't need to reinstall the package. The package is on your computer. It's just loading it into a session to use each time. And one way that we do this in our RStudio environment is oftentimes with something that's called a setup chunk. So you can see we have this command here, this load library for the tidyverse. All right, now, what is this tidyverse? I've been talking about it a little bit. It's a suite of tools for data science. It's not the only suite of tools, but it's a very opinionated suite of tools. Now, one of the key things about performing and carrying out data science is something called exploratory data analysis. And this is a concept that's been pioneered in the statistical field, which is a series of steps beginning with importing your data, cleaning up your data, or making it called tidy, and then transforming your data, visualizing it, applying some models, transforming visualized model, and so on, until you this is a process described as rolling around in your data, until you can extract some insight, at which point you can then communicate. So the nice thing about the tidyverse is it has a series of different packages that address each one of these different steps. And so we'll be able to show you two of these packages today. One package is this import, this is called reader. We'll tell you a little bit about the package called dplyr today, and specifically the select and the filter verbs. Also, visualizing is using ggplot 2, and we'll go over how to visualize a little bit today as well. We won't go into any modeling, but you can see that here are some, and there are several other types of functions and packages that really allow you to carry out every single step of the data science process. Now, one of the unique things about the tidyverse and the series of tidyverse packages is something called the pipe, and it's called a pipe operator. So this is quite simply a picture of a pipe, and the artist, René Magritte, says, "Ceci n'est pas un pipe," which really says, this is not a pipe. And it's a bit of a tongue-in-cheek way of saying, well, it's not a pipe, it's a picture of a pipe. But the pipe is an operator that is used in computer science that is now heavily used in the tidyverse, that is going to allow us to perform a series of sequential steps on data. And when we see this pipe operator, which is this a percent sign, and then this sort of chevron here, and this percent sign, when we see it, we can say and then. So I want to show you a couple of examples here about how the pipe operates. But really what I want to show you is first apply to a couple of simple and silly examples. Okay, so the first would be a series of steps that you would do before you go to work. So the first thing you would do is wake up. And what do you wake up? You wake up self. And then you put on clothes, and then eat breakfast, and then go to work. So if you noticed, as I read through this, I said wake up self, and then put on clothes, and then eat breakfast, and then go to work. So we can think about this as a series of functions that are sequentially applied to an object. The object here is self, and we do different things to the self in sequence. First, we wake up self, then we put on clothes to self, then self eats breakfast, and so on. Okay, now there is an alternative way to write this, and this is much more common, I would say. And this is called nested code. So we say go, eat, put on, wake up, self, nest, close, breakfast, to work. So you can see that it's nested, which means we start with this wake up self here, and then we put on clothes, and then we eat breakfast, and then finally we go to work. While this might be a little bit more efficient, it certainly is less readable. So one of the pop quizzes that I often like to give to people when we present this live is this pop quiz here about what we think is going on here. Now, we'll work through it together. We could say wake up self, and then put on clothes, and then eat breakfast, and then FMK, and then go to work. And I like to ask the attendees what they think FMK is. And oftentimes we get some sort of wild and highly creative acronyms, what people think FMK is. And there's two things that are important here. So the first is, you don't need to know what FMK is to get the general sense of what's happening in this series of piped functions. Now that's important because you will be reading code and you will then get to see that there are examples that you don't totally understand. And if you don't understand something, that's fine. It doesn't make you come to a screeching halt. It just means that you need to come back and think about this. It turns out I thought FMK would be find my keys. One clever and creative student said FMK stands for feed my kitten. So whatever you think it is, it doesn't quite matter because there will be opportunities and examples that you are reading over code, and you can then say, well, I don't know exactly what this means. I can go look it up, or I can look it up later, but I can still get the sense of what's going on. And Denise says, finish my coffee. Very good, Denise. Thanks for that. So, okay. Now, if we look at this again, we see that there's a slight modification. We wake up self, we put on clothes, eat breakfast, finish my coffee, go to work. But we can assign this to an object. It's a little bit different. So this object is now called morning routine. And this morning routine could be something that we could then do again, or it could be something that we sort of save the output of this. So again, we can take all of these different commands and we can then assign that to an object. Right now, a little bit more of a data science example. So we have a CDC data set. Akshay will tell you about it in just a moment. And you don't know anything about this data set, but you can then read through this with me together and get a sense of what's going on here. So we take the CDC data set and then we select distribution state, and then group by state, and then summarize mean distribution. So I'll ask, just to have you guys, if you have any wild guesses, go ahead and put in the Q&A if there's any thoughts or guesses about what this piped series of functions might do. So we take the CDC data set and then select, and then group by, and then summarize. The nice thing about the Tidyverse series of packages is that the intuition for the function names is quite high. We might not know exactly what select does, but we could take a pretty strong guess. Select is going to select distribution and state. I haven't told you anything about group by, but if you have now distribution and state, you might then group by state. So Rebecca and Devi both chimed in. Claudia also chimed in. And yes, you guys are absolutely right. We're grouping by state. And then what we're doing is we're taking the mean distribution here of each state. So again, you guys are sort of burgeoning data scientists. I haven't told you anything about these functions yet, but you can still see and you can get a sense for what this series of functions is doing. Okay, now, importantly, writing code is not like the famous meme about drawing an owl. So how to draw an owl? First, draw some circles, and second, draw the rest of the owl. This is not data science. Data science is more like this. This code is a stepwise process. And when we pipe these together using the tidyverse pipe operator, we can then say, first, we build a base, and then we start to build some of the structure, and then we finish the walls, and then we build the roof, and then we move in or something. That's what data science is. And that's how we can think about this very specific sequential series of steps for performing these operations. So at this point, I'm going to hand the lecture over to Akshay. And Akshay is going to take a moment to tell you about two of the packages. One is going to be a dplyr, and then he's going to show you a little bit about the power of the visualization tools within the Tidyverse. So, Akshay, it's all yours.
Thanks, Matt. You see my screen?
Yes.
Great. So we'll begin with a brief introduction to the dataset we'll be using for the next few slides. So the CDC dataset contains data that we've downloaded from the CDC website itself. And as you can see here, it contains information on the provisional death counts that are updated weekly for each state. And it also contains some useful, in addition to the geographic information, it contains some useful information on demographics, specifically the race and Hispanic origin of the decedents. So So we'll begin our exploratory data analysis by using some simple but useful functions. We'll begin with dim, and dim is a simple function with a simple output. Dim stands for dimensions. And so if we just run it here and look at the output, it's taking just a second, we see that we just get two numbers. Since this is a rectangular data set, it has rows and columns. And so dim gives you the number of rows, which is 185, and the number of columns. One point worth mentioning is that whenever you see rows, always think observations, because in a tidy data set, each row corresponds to a unique observation. And whenever you see columns, think of variables. So dim is useful, but limited. A more useful function or a more comprehensive function is glimpse. So we just run glimpse, and we see that in addition to, so for one thing, it's more, its output is more specific than dim's output. So in the case of dim, you just see two numbers. Here, it explicitly states that the first number, 185, is the number of rows, and the second number is the number of columns or variables. And it also shows you, importantly, it shows you what those variables are, the first few entries for each variable, and some information about the variable itself. So someone asked in the Q&A, is each object, or in this case, each variable, associated with a class? And the answer is yes. And this provides that information. So there are many data types in R. We will just mention a few here. So there's a character data type. So that could just be a name or a letter, so anything in quotes. Numeric is a number. Now this could be a whole number or a number with a decimal point. There's an integer, which is a whole number. And it's in R, we tell R that a number is an integer as opposed to numeric by putting this big L after it. So if you see that in your environment, you know that R considers that to be an integer. There's logical, which takes only one of two values, either true or false. There's complex, which is composed of a real part and an imaginary part. And then there are some more exotic data types like raw, which is highly unlikely you'll come across it, but it's good to know that that exists. One thing worth mentioning is you will see this data type double. Actually, we see it in our data set here, DBL. Now, it's not technically correct that it's identical to numeric, but for our purposes, when you see double, just think numeric. And finally, the final data type I want to talk about is a factor. Now, a factor is a collection of ordered character variables. So if you think, for example, of a list of names, and you know nothing about the names about the people, the names wouldn't necessarily be an ordered list. It would just be a collection of names. But when you think of the months of a year, they're definitely ordered, January, February, and so on. So factors is an important thing to know about. So this relates to something we brought up earlier and a question that someone had about the type of variable. So if you want to see what kind of variable you're dealing with, you can use, as Matt mentioned, you can use a $sign to extract that variable from your data set. So in this case, CDC. In this example, we want to see what the class of state is. So we do CDC $state, and we use the class function, and it tells us it's a character. Now we can choose another example, or you can see what the class of distribution is. And it's a numeric. So actually, this is an important point. So it says numeric here, but if we go back, it says double. So this is where it could maybe get a little confusing. But like I said, for this, in this case, just think of them as identical. So I'd like to reintroduce this pipe concept that Matt mentioned, just because it's so useful. And once you get used to it, it makes coding very intuitive. So again, just to reiterate, in this specific example, we take CDC, which is the name of our data set, and then. So when you see the pipe symbol, you always think and then. You pipe it into the select function, and the select function selects these two variables, and then you pipe that into the filter function, which only chooses states that are Kentucky. And we finally pipe that output into this head function. So this head function is not super important to know right now. We just included it here so that we can see ideally all our output on this one screen. So head just shows you the top few rows of your output. So here we see that we've selected just state and distribution, and the only states we see are Kentucky because that's what we filtered on. So this slide just basically describes what I just said. The key thing to remember from this is when you see this pipe operator, think and then. So as Matt mentioned, the alternative to chaining a bunch of lines with the pipe operator is to just nest everything, put everything in one line. And this line here, this filter, select, and so on, is perfectly fine and gives you the same result as the previous chunk of code. But there are, for one thing, it's a little difficult to read, it's a little difficult to write, and it's error prone. So getting used to using the pipe and using the pipe is definitely beneficial. So the first package I will briefly introduce you to is the dplyr package. And the dplyr package is one of the workhorse packages of the Tidyverse universe. And it contains functions that enable you to do lots of useful things with your data set. You can, as we've seen, you can choose specific columns, specific rows, but you can also generate new columns and rows, and you can do fancier things like create summary statistics and things like that. So for this class, we'll just go over select and filter, but know that there are many other very useful functions. Some of them have been listed here. So the select function, as its name suggests, or rather indicates, it selects one or more given variables. So in this example, we take CDC and then we pipe it into select and select the two variables state and distribution. And we also use this head function just to see what the top few rows are. So in this case, it's cut off on my screen, so you can only see the top row. But again, you've selected just state and distribution. So it's simple, intuitive. If you want to do the opposite, if you want to select everything except a given variable, given variables, you can use this minus sign. So in this case, what this code does is it takes CDC and it selects everything except the state variable. So you see instead of 5 variables, you have 4, and the one that's missing is state. Now, if you have many variables you want to select and they all happen to be in a row, instead of one thing you could do is you could just type them all out. But what you could do is, if you know for a fact that they're all in a row, you can take the first variable and the last variable and put a colon in between and put that in your select function. So in this case, I want to select everything between state and distribution, including state and distribution. So if I run that, I see, so in this case, it's a small data set, so I could have just written out all 3 because the only variable that's in between is ethnicity. But if you had 100 variables, this would be a lot more useful. So that's select. Filter, so you have to be careful here. I often say filter is used to select rows, but that's a contradiction. Filter is used to choose rows based on some kind of logical statement and or logical condition. So we can use filter to, so filtering can be performed on categorical data. So in this case, we take the CDC data set and then we pipe it into the filter function and it will only it will only choose states that have the name Kentucky. And the way we do this is we do state, which is the name of our variable, and we use this equal to sign. And then we put Kentucky in inverted commas. And the reason we do equal to is that's asking R if a given state is Kentucky or not Kentucky. So it'll produce either a true or a false. And for every instance where it produces a true, R will choose that row. And if it's false, it'll discard that row. It's very common to just do equal to. Now, Matt showed you earlier this arrow sign, this left, pointing to the left. Equal to is, you can use equal to instead of that left operator. I don't suggest doing that because the left operator is a lot more explicit, but that's what the equal to does. It assigns something to something else, which is not what we want to do here. So let's just copy paste that to see that it works. And yep, this only produces the first 3 rows, but you can see they're all to do with the state Kentucky. you can also perform filtering on numeric data. So in this example, what we're filtering on is the variable distribution, and we're only choosing those rows for which distribution is greater than 2. So we can run this. And again, we only see in this case, the top 2 rows. And if you look at distribution, you see 53, 23, they're both above 2. Now you can chain, this is where the pipe operator shines. You can take in our previous code, and let's say you want to filter on both those conditions. You can chain them like this. So you can put them one after the other and link them with this pipe operator. So this is identical to the previous 2 chunks of code, but put together, combined. So we take the CDC dataset, and then we filter on states that are Kentucky, and then we filter on distribution that's greater than 2. So if we run this, we see, again, just the top 2 rows. The state is Kentucky for both, and the distribution is greater than 2. Now, if you had multiple conditions, so what you can do is you can either do it like this, which is a perfectly valid way of writing your code. It's very explicit, easy to understand. Each line just does one thing. What you can also do is you can take those 2 filter statements and put them within one filter function and just separate them with a comma. So this is the same as this, except we use just one filter function. And just to confirm that the output is the same as before, oops. This is the output here, and previously this was, so we can see the output is the same. So that's dplyr, and it's really just scratching the surface of what this package can do. The next package will be ggplot, and we'll begin with this quote by John Tukey. The simple graph has brought more information to the data analyst's mind than any other device. So graphs are useful. So the package we'll be using is the ggplot2, and the GG in ggplot stands for grammar of graphics, which is a system of rules that are used to make pretty and informative plots in R. Now, the bare bones of the code you need to use ggplot is really just this. You start you always start with the ggplot function itself, and in this case, you can put your dataset, the name of your dataset within ggplot by doing data equals the name of your data frame. So in our case, it would be CDC, and then unlike so what the ggplot function does is think of it as creating a canvas, a blank canvas for your eventual plot. So if you just run ggplot, all you'll see is a blank canvas. So we then need to tell R to put something on this blank canvas. And for that, we'll use geom functions. But before that, so just like with dplyr, ggplot also has a kind of chaining operator. But instead of the pipe, we use this plus operator. It's somewhat similar to a pipe, but I think of it as adding layers. So we start off with a blank canvas, and then maybe we add a scatterplot. And then on top of that, we add labels. And on top of that, we add a title for our plot, and so on. So in this very simple case, we do plus and the geom. Now the geom defines what kind of plot we have. Is it a scatterplot, boxplot, so on. And we also need a mapping. And what mapping does is it tells R which variable to assign to, if it's an XY axis, the x-axis, and which variable to assign to the y-axis. And we put the mapping to the x and y within this aesthetic function, AES. So to see this in action, this is a simple example of a scatterplot. And again, we begin with ggplot, and we tell it what data frame we're using. So data equals CDC, plus instead of pipe. And the specific geom we're using for a scatterplot is geom underscore point. And we'll see what the geom functions for other plot types look like. And within geom underscore point, we do mapping equals AES, so aesthetic, that function. And then we assign the variables. So in this case, we're assigning weighted distribution to the x-axis and distribution itself to the y-axis. And we see, so weighted distribution is the distribution of deaths weighted by the population, by the underlying distribution of the ethnicities. So you would expect, if there were no bias, you would expect this to be a nice one-to-one relationship. But clearly, they are positively correlated, but there's quite a bit of dispersion, which could be meaningful. So just to break up this piece of code, you start off with ggplot, so you initialize with ggplot data equals CDC, and then you start adding your layers. In this case, we've just added one layer because we just have a scatterplot, and that's geom point. There are whole books dedicated to ggplot and conventions, plotting conventions and things like that. But we will mention just one thing, and that's where to put this plus sign. Now, you could put this whole code just on one line. You could put the plus sign at the start of the next line. Both are frowned upon. It's best if you do it like this, as is shown here. And when you look at lots of other people's ggplot code, this is how they do it also. Now we'll just touch on the concept of these other of aesthetics, and we won't actually show you any examples, but there are these various aesthetics from color to fill that allow you to not just map your data onto, like in the case of a scatterplot, points, but onto other things like color, for example. You could map your state variable onto color so that you have different colored points associated with different states. And similarly, for size, you could have all the data points that correspond to North Carolina as diamonds, and all the data points that correspond to South Carolina as circles, something like that. And there are others, alpha, that controls you can use to control the transparency. Fill and color, very similar. So that's worth mentioning. Now, the real power of these aesthetics is, well, I think, to map your data onto your plot. But you can also just say you want the color of all your data points to be red instead of blue. That's also doable. So there's this concept of global versus local mapping. So in this example given here, the mapping is done within the geom functions. So in this case, we have two. In the previous case, if we look at this as just one layer, just geom point. In this case, we've added two layers, and there's no geom point. There's geom jitter, which I'll talk about in a few minutes, and geom boxplot. But we've put the mapping within these geoms. We could just as easily, instead of repeating this, since it's the same information, we can take this AES and so on, and put it in after CDC. We can do comma and then AES. Similarly, we can remove it from the boxplot, so there'll be nothing in there. I should say, I think I missed something. Okay, sorry, I skipped this bit. Previously, we said, data equals CDC, mapping equals. In this case, we just show CDC and AES. So you don't actually have to explicitly state data equals and mapping equals. You can initially, just to remind yourself of what goes where. But once you get familiar with this, you can just put in the name of the data frame and the mapping without actually saying data equals and mapping equals. So there's this question: how are these two plots similar? Well, they look like they've been taken from the same data set, which we know there's only one, CDC, and they're the same variables being plotted against each other, distribution and weighted distribution. The only difference is the geom. So in this case, we use geom point to make a scatter plot, and in this case, we use geom smooth to fit a model or to fit a line. And so this is the code for, in this case, plot 1 and plot 2. So for plot 1, which is a simple scatter plot, it's like what you saw previously. Plot 2, so there's a mistake here. ggplot should have CDC in it, not weighted distribution and distribution. But ignore that for a second. So plot 2 is basically the same as plot 1, except instead of geom point, you have geom smooth. So this shows you how easy it is to convert from one plot type to another, just by making this small change. So you need to know, obviously you need to know what kinds of variables you have to decide what types of plots to make. So in this case, you can see the scatter plot only really applies to distribution and weighted distribution, because those are the only numeric variables or doubles. It can get tricky when you start, especially when you start off, to know what geoms to use. So to do that, there are these handy cheat sheets that you can get from our studio. There's one dedicated to ggplot. And this just has a collection of other cheat sheets. And there's this excellent resource called Data2Viz, which you can use. You can start off with a given data set, and it will provide you with guidance to help you decide what is the best way to show this data, to show your data. Like, for example, do you have two numeric variables? Do you have three? And depending, are they ordered, not ordered? Depending on the answers to these questions, you have this nice flowchart, and it will show you what to pick. So let's say I wanted to make a violin plot. It tells me what a violin plot is. But more important, or just as importantly, it shows me examples of these violin plots and also the accompanying code. So this is a really useful resource to learn how to make different plots. All right. So the question is, how do we change this to a box plot? So I wanted to say that, so we can see a little X here. So R clearly doesn't like something. So what it doesn't like here is the fact that this variable weighted distribution has a space in between weighted and distribution. So that tells us that when we're naming variables or naming things in R, it's best to not include spaces. So ideally, this should have been weighted, maybe underscore distribution, or just weighted distribution as one word. So to handle this problem, we can just put weighted distribution within backticks and run it. And we get this kind of plots. Unfortunately, the bottom half is cut off, but we see that this is probably not the most appropriate way to show this data. So if we wanted to show this as box plots, which is an appropriate way to show it, all we have to do is replace geom point with geom boxplot, and we can run it again. And we get an output that's a lot more meaningful. So what would this code do? So we have ggplot, and then we have geom boxplot and geom point. So predictably, actually, we can see what it does. We can copy paste it into this chunk. And again, remember, because weighted distribution isn't properly named, we have to put it within backticks. When we run it, we see it's taking a little while to run. What it does is it first plots. So the first layer here is your blank canvas. The second layer are the box plots. And then your final layer are the individual points themselves. So you can see how easy and intuitive it is to start from something simple and make it more complex and sophisticated. So that's it. That's a very, very brief introduction to dplyr and ggplot. And I hope this gives you the motivation to do some more exploration.
All right. Thank you, Akshay. So I did want to just conclude, actually, today's session with just one more key idea. And then just point you to a few resources that will help you continue this data science journey, this introduction to data science. So the first thing really is this concept of reproducibility. And so we've sort of set up this concept of data science, and Akshay showed you a couple of examples where you can take a data set and you can apply a series of transformations to it. That series of transformations can then be piped into or directly called into ggplot for some visualization. But the most important and perhaps powerful part of all of this is that the reports that can be generated and the reproducibility. Akshay showed you that there's the ability to basically press run, and it performed a series of calculations. And so I just want to leave you with this idea about one part of the R programming environment, which is something called R Markdown, and this is its own type of language. So the scientific reproducibility and data provenance, meaning where do the data come from, is on everyone's mind in the scientific and biomedical space these days. And one way that R handles this, and one way that data scientists handle this, is by having something that's called an R Markdown document. So I won't be able to go into, again, the details and the specifics, but I want to show you really what the power of this looks like. And so the R Markdown is a plain text file, but importantly, it has three different types of content. So the first is going to, we're going to start in the middle here. The first is just text. And this text can be written in a language that's called Markdown. It's a quite simple language. You can bold, you can italicize, you can make a numbered list, etc. And this is going to be text which we can then write in a report that will be about some data science or some transformation that we just did. But then importantly, the second type is what we call the code chunk. And we've shown you a couple of code chunks embedded within the slides that we've broadcast to you today. And these code chunks then are going to allow you to run the code directly in them. So the power of these R Markdown documents and the reports is the interspersing and intermingling of text and code and text and code. And really, I could write an R Markdown document and I could send that to Akshay, or I could send it to any of you, and you could then run that and have it perfectly reproducible. The third part is this YAML header, which is then going to be a title, and it's going to be some specifics about how you want to output it, whether you want to output your R Markdown document as a PDF, as a Word document. Perhaps you have a colleague who is not as sophisticated as you all now are in data science, and you want to share a Word document. You can then what's called knit. You can knit your RMD into a Word document and share that. And so the most important and I guess key part of this R Markdown is the reproducibility. And so Siddharth actually just asked a question that Akshay will answer, but I'll also just mention it right now about intermingling R and Python. So Python is one of the computer programming languages that is oftentimes used for data science. And several of the subsequent lectures in the Symposium will be discussing Python and giving you some of the details of the Python programming language. And the interesting thing is there are packages that allow R and Python to basically communicate with each other. And in fact, you can run Python code chunks within R Markdown documents. So much of this sort of intermingling and reproducibility that is key. If you get something from a collaborator that has a Python script that you want to run within your sort of data science environment, then you can do that certainly within this R Markdown. So this R Markdown really is one way to achieve this reproducibility, and that's then what I call this knit button. So we can knit to render a report. So on the left-hand side of the screen here, we can see the R Markdown document, and we have a little bit of a header, and the code chunks are in gray, and then some text and more code and so on. And on the right, it shows you what the rendered report actually looks like. We can see that there's a title, we can see that our code chunk is here, and we can see the output of our image, in this case, they're just called in this code chunk called image. And so again, you can then share this code chunk or this RMD with somebody, this document with somebody, and they can then render and run the same thing. And the power, again, of this comes that you can really convert it to a multitude of different documents. And the way it works under the hood is to take this R Markdown, it knits it into what's called Markdown, and then this other layer called Pandoc. The details aren't important, but Pandoc can then take this Markdown and convert it into plenty of different file types. So again, I just want to nail these key points that it really allows you to take this R Markdown document, this data science session that you had, it then can knit these and render them all together and share that with colleagues. Now, of course, just like the dplyr resources, just like ggplot resources, R Markdown has its own resource. So there's an entire book written about R Markdown. Again, one of the best things about this ecosystem and this community of R developers is everything is free, everything is open source, and so on. So you can find this R Markdown, the definitive guide, and this will really dive deep into the R Markdown programming language. Okay, so then there's a couple of final concluding thoughts that I want to share with you before we wrap up here. So data science as a field is really remarkable. I came from a background of chemistry and biochemistry and then some physiology, but really I got interested in data science when I realized that data science enables this data-driven information gathering and hypothesis generation. And so this can be for scientific research, this can be for reviews, this can be all sorts of different questions. And really, on this third point, that data science is process-centric. not necessarily question-centric. So if you have a very specific question, you can apply a set of data science tools to that question. If you have a different question, let's say in a totally unrelated field, you can apply the same types of data science tools to it. So for example, my lab studies sort of the molecular inner workings of cells and how that leads to disease. We can apply some of our data science tools that we use to looking at COVID-19 data to make some insights, to make some graphs, to help understand the tracking of the virus and the tracing of this pandemic. Data science also enables the ability to ask new types of questions. And so again, this process of exploratory data analysis and what I called sort of rolling around in the data, really it allows you in a highly unbiased way to come up with new types of questions that might not otherwise have been possible or in the front of your mind. I also think an important point is making things computable makes them actionable at zero marginal cost. And what I mean by that is that when you make something computable, and when you are applying computation to a project or to a process, that you can make them actionable and you can get insight into them at no cost. Of course, you have your time, but this is not like making a widget. This is not like trying to invent a product. This is something totally different. That software is scalable at zero marginal cost, and this is really remarkable. And then finally, the last point I want to make is data science enables us to generate workflows that save time and also achieve reproducibility. So this was just scratching the surface and really giving you all an introduction to data science today. And I want to point you to a couple of resources. So of course, RStudio has fantastic resources. I would encourage you to go to RStudio and look at their cloud environment, look at their cheat sheets, really to understand what's possible. Of course, Google. Google is also quite simple. You type in Google your error or your question, and you will get a really rich a community and resource of answers. There's also a fantastic book. Again, this is online and freely available. You can also buy the book if you want a physical copy. But this was a book that I started with very early on. It's called R for Data Science. And there's a website associated with it that has all of the same content as the physical book does. And this will give you, again, if you look on the left here, introduction to data science, data visualization, workflow basic, data transformation, and so on. So this is a fantastic resource that I would encourage you to look up. And then lastly, there's two resources that Akshay and I have been co-developing and really trying to make. So we started by saying that we want to bring the Tidyverse to graduate students and medical students and people studying molecular biology who oftentimes don't have this training in data science. So we started a small project called Tidybiology, and we have a little website where we're putting a bunch of our instructional videos and our GitHub repositories and so on. I saw some questions in the Q&A about GitHub repositories. All of this is on GitHub. This is all online, and I encourage you guys to access it. I would also point you to the Tidybiology videos. We have a YouTube channel, and the YouTube channel is going to host this video, but then also we have several other videos. I'll just say one example was a few months ago, we worked with Larry Karen and the PlusDS group to give some more in-depth lectures of this introduction to data science. And we recorded all of that, and all of that is available. So then the last thing that I'll say is I just want to acknowledge Akshay, who's instructed this with me, but then also importantly has developed a lot of this content with me. And then part of the ethos of the ecosystem, this R ecosystem, is to both use others for inspiration, ideas, package, and code, but then also acknowledge them. And so I'd like to acknowledge the R for Data Science team. I'd like to acknowledge several people who have developed fantastic resources, who have thought deeply about how to teach R and how to teach the Tidyverse. And then lastly, I'd like to thank you all. So there are literally hundreds of you who have stayed this long. So thank you for your interest. We will stay around and answer any possible questions that come up. So if there's questions, go ahead. You can chime in on those now. But then the last thing that I would like to point out is that our lecture here is just the first in a series of lectures. And so you can see today is June 30th, but then we have this amazing program that has been put together by this collaboration between Duke Science and Society, between Larry Caron's Plus DS group, between several different people who have come together to really try to have a very simple question, which is how do we make sense of this abundance of data that is essentially fire hosing us from COVID-19 and the virus. And so we have lectures you can see coming up on using natural language processing to mine literature. We have some deep learning coming up using PyTorch. We have some image analysis using chest CT scan data. We have some ethics questions and ethics discussions. We showed you, and Akshay mentioned quite briefly, that there are disparities in people of different races in different skin colors who are seeking access or who have different susceptibilities to COVID-19. And so what is that about, and how should we think about that? So the ethics is going to be a really important part of this conversation. You can see that there's several others, so I'd encourage you to register for those if you're interested. So thank you for your attention today. And again, we'll stay around for a few minutes to answer any questions and post them on the Q&A board.